Hey everybody, Omni Griffin here, and I wasn't kidding. I just hit stop and start. So, what we need to do is we need to step up if our current location. See, here's the thing. Yeah. Hers is set to 80. That's bad. Alright, if where we are equals a data cube, and mem1 equals nothing, or where we are is less than memory 1, memory 1 equals where we are. So once again, I don't actually know how this if statement is working. I know where I want the parentheses. I really need to just like show why this is important. So if where we are is data cube and either memory 1 equals nothing or where we are is less than memory 1. So I want this and one of these two things. So we'll see. If above us equals a wall, if above us is a wall, pick up mem1, give to mem2, that's fine. Okay, that didn't work the way I wanted it to. Can any of these be 0? Yes. Shit. Actually, no, that'll work. That'll work. Actually, does not equal data cube. That didn't work. This should work. No, it's not. That 0 is actually going to break everything. Yep. Oh gosh. Okay, so if where we are is a data cube and memory 1 is 0 and memory 1 is not equal to a data cube or memory 1 is greater than where we are. Okay, this is the one that has the 0. Okay, I think we got it. Whoops. That's how this needs to go. Actually, it doesn't matter. This jump can just happen. Oh my! There we go. We need to clear memory. That still didn't work. Alright. You. Alright, he goes here. If where we are equals a data cube. Okay, he didn't store the 30. See? Oh, that's annoying. So this is actually a really good depiction for why... Okay, it worked. This is a great depiction for why, why things get really wonky. Oh, wow, we got the commands. We didn't quite get the speed, though. That's okay, we can make this faster. So... yeah. How do I describe this? So there's this concept in computer programming that, if you're not familiar with it, is really weird, and that is the concept of null. So how do I put this? I'm trying to figure out how to phrase this. Give me a second to blow my nose while I think. It's funny, because for you guys, it feels like I've been sick for weeks, but I've just been sick today. So, as I get my next lozenge. Null is not 0. It's truly nothing. So, if you have no candy, you have 0 candies. And that's why it's weird. Because that's how you think about it. Like, I don't have any. It's more like the bag of candy, right? So, if you have a bag of candy, it has some amount of candy in it. It can have 0 candy in it, but it can also have a billion candy in it. But you can also not have the bag. And when you don't have the bag of candy... obviously, this breaks from reality in a little bit, but you can't have any candy if you don't have the bag of candy. So, therefore, not having the candy is null. Like, that is null. Not having the bag, because then you can't have candy. You can't possibly have candy because there isn't a bag for you to have candy with. There's just nothing. And that's where this is getting weird, because what we can do now, and it'll make it a little bit easier, maybe, is we set memory 1 to nothing. Alright, well, here, we're gonna do Alright, so if where we are is a data cube and memory 1 is greater than where we're at. Okay, I actually am curious what happens with nothing. Okay, yeah. So whenever you're doing things with... So nothing here is null, and 0 is 0. So nothing gets a little bit weird. Okay. Oh, right. You need to be consistent. Depending on what programming language you're using, things can be a little bit weird with null and 0. Some languages can effectively interpret null as 0. Or 0 is null. This is actually a little bit slower, believe it or not. Oh gosh. So here's the weird part. We can change this. So what we can do, so if where we are is a data cube, set memory 4 to where we are. Memory 4 is going to be our last data cube. Which is going to be a bit weird. We're going to set memory 3 equal to memory 4, and we're going to set memory 4 equal to this. So basically the last two ones that we've run into, last two things are going to be there. So okay, this needs to change a little bit. Alright, we're going to do one loop. So we step up. If we are as a data cube, we store it. Then, if memory 1 equals nothing, or memory 1 is less, where we are is less than memory 1, set memory 1 equal to where we are. Simple enough. Okay. This is the first loop, actually. So we're actually going to be splitting this into two loops for a couple reasons. If... Okay, so I think this is all the memory manipulation we need to do. So we're going to be storing the last two blocks that we've seen right here. If above us is a wall, we pick up memory 1, and then we give that to memory 2. That's pretty normal. And then we're also going to set memory 1 to nothing. Boom, done. If we do this, it should work. Okay, we actually slowed down a little bit, and that's because we're putting in some overhead right now, which is this extra data storage that we're not taking advantage of. So, if above us is a wall, that's actually not what we want to be looking for. So if memory 4 does not equal nothing, this is actually still in here. If memory 4 doesn't equal nothing, so if it, let's think about it this way, it's easier. If memory 4 is a data cube, okay, this actually is different. We have to pass this jump. So this is storing the last two. So when we hit here, when we hit the wall for the first time, we'll be storing the last two. We actually do need to sleep. This shouldn't make enough of a difference. If we're like a second off, then yeah, we'll switch this jump out. But it's only going to happen once for each person. So, now we have the last two set. I'm actually curious what happens if the last is the lowest. This doesn't work, does it? No, it doesn't. It might. It might. Oh gosh, this is gonna... The way I'm trying to optimize this is to basically prevent us from having to walk all the way to the wall every time. Because I think that's where our biggest time save is gonna be. So I'm trying to figure out how to do that, and it's by doing this memory shenanigans. So in here, we're still kind of running the same loop. We might have to build some protections in here. But we're building the same loop here. So we've dropped it off, so we need to step up. We're always going to have to... So the fun part is we're always going to have to step to memory 4. I think it's equally as efficient either way. This way is probably just as fast. So we step up. We do the same thing. If where we are is a data cube, then and memory 1 equals nothing, or where we're at is less than memory 1, we set memory 1 to where we are. Seems pretty good to me. This is going to be about what we were doing before. This is what's going to change, but I'm going to do this just for my own edification here. This should still work. But it works in the exact same way. Okay. See, we didn't really... We got faster for some reason. I don't know why. So. I'm going to say it's not any faster than doing this. But here's the thing. We're using this memory 3 and memory 4, and it's supposed to be in an advantageous way. It's going to basically fix this for us. So, if where we are is a data cube, and it's one of those things, cool. If where we are equals memory 4, if we are on the last thing, then we pick up memory 2. Here's the problem. When the last one is the highest, or is the lowest, and I don't know what's going to happen there. I need to see what happens when we shred memory 4. Okay, good. It's going to happen with this one right here. So as you can see, 16 is the lowest right now. That's about to change. We have the shredder. We also have the second to last and the last. So we hit the wall. Okay. Set memory 1 to nothing. Memory 4 is... Huh. Interesting. 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 That is not what I expected to have happen. Okay, what happens if I don't set memory 1 to nothing? You. Okay, it's getting set to nothing anyway. That's good to know. It's a shame that they don't initialize to nothing. I guess I'm the one who has to do that. Alright, so. Here's the wonky part. This. Right here. So. We have to do a little check here. We're going to have to do it in other places too. If memory 4 equals nothing, set memory 4 to memory 3, and memory 3 equal to nothing. So yeah, this is going to get a little weird. Believe me, I know. Alright, Alright, so now we need to break this up. If where we are is data cube, if memory 3 is nothing, we set memory 3 equal to where we are. Sorry, I should say if memory 3 equals nothing, and where we are does not equal memory 4. So we don't want to accidentally overwrite. So basically, if we have an empty... No matter what happens here, we will always have a memory 4. But we might not have a memory 3. Because memory 3 is the second to last. Because if we're keeping track of our last and our second to last, and we delete our last, we only have a second to last. So we move that to our last in memory, which is memory 4, and then we clear out our second to last. And so then we store it until we hit that. And then weird stuff happens. If memory 1 equals memory 4. So if we're going to delete our last... Actually, no, we already... We don't need to set it to nothing. If memory 4 equals nothing, we set memory 4 equal to memory 3, and we set memory 3 equal to nothing. This should short circuit us from hitting the end of the wall. If this doesn't make any sense, believe me, I understand. This one, no. Do we have any of these where the lowest is the last? I think the answer is no, but this is the closest one. So let's follow him on his adventures. So he's just going to keep moving up. We're storing the latest ones we've seen and the lowest. So 6 is going to hold into the lowest. And this is our first half of the loop, so we do have to go all the way to the ceiling. But we have our last 2 stored as we expect. Okay. So memory 4 doesn't equal nothing. We're not going to be able to test this code just yet. Okay, so now we're in our second loop. So we are then going to run back up. We're going to store our lowest. And this... Okay, he's going to commit suicide. So we're going to... Something's wrong with our code. We'll figure it out. So if where we're at is a data cube, it is. If memory 3 equals nothing, we don't have to worry about that. If memory 1 is nothing or where we're at is less than memory 1, which it is, we set it. If where we are equals memory 4, we are on the last thing. Pick up memory 1 and give to memory 2. If memory 4 equals nothing, which it doesn't, crap. So that's the problem with our code. Okay. We can do this. Because then it runs here multiple times. Alright, do we have anybody where... Okay, this one. We can look at our first bit of the code. So, first time around, we're going to have to run all the way to the wall. I'm going to feel really silly if this doesn't actually make it faster. Okay. We pick up 1, give to memory 2. If memory 4 is nothing, which it's not at that exact moment. Oh my god. I think we actually need to do this because we need to burn time. We actually need to burn time. This one still. Alright. So we pick up memory 1. Done. We go to memory 2. Set that to nothing. Jesus. This is frustrating. It's really frustrating because that's one of those things that I can't. We have to have another special if statement because we don't spend enough time. The 20 hasn't been destroyed yet. Oh god, this is a really bad, like, it's like a garbage collecting problem. I don't want to run this if statement every time. Yeah, we're just gonna have to run this. If memory 4 equals memory 1, set memory 4 to nothing. Actually, set memory 4 to memory 3. That actually makes so much more sense, because then we don't have to do this if statement. Oh, and we do have to set memory 3 to nothing. Okay. Let's try this again. Good, you're the one with the lowest at the end. So we gotta go all the way up to the top. Alright. Pick up memory 1, we feed it to memory 2. If memory 1 equals memory 4, it does. We set memory 4 to nothing, or to memory 3 to nothing. Beautiful. Exactly as it should be. We step up until we're at a data cube. Okay, and this is where things get interesting. So if we're at a data cube, yes we are. If memory 3 equals nothing, and where we're at doesn't equal memory 4, actually we don't care if memory 3 equals nothing, because now memory 3 is going to be 18, which is going to cause problems. Yep. Okay. If where we're at doesn't equal memory 4, we set memory 3 equal to it. Alright. We want another person with the lowest at the end, which I don't think we have. This one's as close as we're gonna get. So, run all the way to the top. Wait, no. We need the second lowest to be... Here we go. This guy. Runs all the way to the top. So I'm covering his actual memory with my hands. So right now, memory 1 should be 2. Oh Jesus. Yeah, no. Memory 3 should be 2, and memory 4 should be 3. Yeah, okay. So he walks up. We keep setting, keep setting, keep setting, keep setting. So now we got 24 and 3, which is accurate. And then 3. So if where we are is memory 4, we pick up memory 1, we give it to memory 2. 4 equals 1, so we set memory 4 equal to 3 and 3 to nothing. Probably actually don't need to set 3 to nothing. Yep, they only go as far as the last one. The question is, did it save us enough time? And if it didn't, I'm gonna be sad. Oh, it didn't save us any time. And we failed a couple times. Okay. Where did it fail? Oh. Shoot. I didn't see why that happened. Oh, double numbers. No. Is it really that stupid? Alright, so the first time we have to go all the way through. Okay, so 13 is the lowest. That's fine. He does some checking. Aha. Yep, our way is broken. Our way doesn't work. Yeah. Yep. That's dumb. So the double number fail is actually surprisingly common based on what we saw. So the problem is now memory 4 is incorrect. So all of this optimization falls apart for 2 reasons. And this is the depressing part. Well, it's mainly one reason, but it kind of manifests itself in 2 ways. So the main reason is it doesn't actually... Oh god, it's doing like shallow compares. So here's the other weird thing when it comes to pointers and what they're pointing at. So when I say 14, because we had 2 14s here. When I say 14... Or when we're checking, when we are checking if where we are, down here. If where we are, what are you? Oh, because I'm breakpointed. If where you are is equal to memory 4, do stuff. Well, here's the problem with that. And I mean, the problem with that... Oh, man. Oh, it hurts, though. Okay, so the problem with that is... It's not comparing correctly. So there's this thing called deep and shallow. And it has to do with what you're looking at. So basically what's going on here is we're looking at the bags of candy on the floor, and 2 of them have 14 pieces of candy. But the only way that we know how to describe those bags is the number of candy that's in them. So 2 bags that have 14 candy in them look the same to us. If you hold them both in one hand, and you put them both your hands behind your back, and you pull one hand out, and you go, here's this bag. Is it the same as? And you put it back behind your back, and you pull out the other hand, this one. And we know that the bag that you've shown us has 14 pieces of candy in it. We don't necessarily know that you didn't switch. You know, you don't only have one bag there, and you just kind of swapped it between hands behind your back. And we also don't care. Because to our eyes, because that's all we're checking is the number of candies in them. We don't care that you might have switched it behind your back. To us, it looks like it's the same thing. So that means when we've got the 2 14s in a row, when we hit this one, we think we've reached this one, and that breaks it. That breaks it. Which means that this entire attempt that we're going for here will not work. So if I were to instead label this as a grid, right? Like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. This would be 2, 5, and this would be 2, 6. And if you were to look at their actual addresses, and I'm putting air quotes around that, you would be able to tell the difference between the two. But the way that these things are stored in memory, that doesn't work. So I'm actually trying to do something that's too advanced for this code. Which, you know what? That's okay. That's okay. It's unfortunate, but that's okay. I think this actually just works, by the way. Because we got rid of the setting things to nothing. Also, I can get rid of some of these, which will save us time. Yeah, we're taking a lot of extra time. Okay, it's really unfortunate, honestly. The weird thing is, though, that it is storing addresses. We're so close. How do we optimize this further? So it's dumb, but it might be enough. What? Oh. Wait a minute. Yeah, I can't even do that. Okay, we've done something that makes the scenario now impossible. Oh. I'm stupid. Oh, come on. I need to save 6 seconds per. Okay, so what we could do... Okay, we could save a little bit of time, but that's it. Oh, I know what we do. I'm dumb. I'm dumb. Okay, so what we're gonna do is we're gonna actually... Okay, I'm gonna do something interesting here. Actually, let's do this. Alright, so here's how this is gonna go. We're gonna store the lowest 3 every time. Every time. And that's how we're gonna do it. And it's gonna go pick up memory 1, pick up memory 2, pick up memory 3. I can't believe I didn't think about this. Alright, so this gets a little bit odd. Alright, so if above us is a data cube, if it is less, so memory 1 is going to be the lowest. If it is less than memory 1, else if it is less than memory 2, else if it is less than memory 3. So this is the lowest, lowest. So if that's the case, then we are going to be setting all 3 memories. We're going to set memory 3. We actually have to do this in a specific order. 3 equal to 2, 2 equal to 1, and 1 equal to that. Plain and simple. If it's not, if it's the second lowest that we've run into thus far, then we set memory 1 is good. We set 3 equal to 2 and 2 equal to 1. No. 2 equal to it. Otherwise we set 3 equal to it. So, if it's a data cube, or memory 1 equals nothing, or memory 2 equals nothing, or memory 3 equals nothing. Alright, I think this will work. So let's watch. Nothing. Okay, so we step up to 81. We're at it. Oh, whoopsie, we've already set 81. 81 is now the lowest. So now we're looking at, I don't know. But it is not less than 81. Remember that 89 is next. But memory 2 equals nothing. It's 86. So now we're checking 89, which is not true there, but that is true because memory 3 is nothing. Cool. So now it's 65 is going to be next. So, it is less than the first one. So, 86, 81, 65. That worked out much better. Look at that efficiency. Alright, now that I've taken way too long for this episode, thank you guys for watching. I'll see you next time, but until then, keep your gears turning.